Hi everyone. In the last few sessions, we discussed how to calculate the radiation energy emitted by an individual body or an individual surface, whether it is black body or a gray body. In today's session, we will try to discuss the radiation exchange between two surfaces facing each other. Radiation exchange between two surfaces is a bit tricky. For example, see the two surfaces which I have shown here, surface 1 and surface 2. Suppose I keep these, assume that they are plates, flat plate. So if they are very large plates and if I keep both plates parallel to each other, then whatever radiation energy which is coming from one surface will completely fall on the other surface. Yes, correct. This is valid when the plates are very large and they are parallel to each other. Right. Another case, suppose I keep the two plates inclined to each other as shown in the figure. It's very even our common sense will tell us that all the energy which is coming from surface 1 will not fall on surface 2. Majority of the energy will fall on surface 2, while some may escape actually because they are not facing exactly each other. Correct? They are inclined. Suppose I increase the angle actually. I tilt it more so that the plates are facing away from each other. What will happen? Still less amount of energy which is coming from surface 1 will fall on 2. Majority of the energy will simply leave actually. Right? Yes. So it gives us a clue that the amount of energy which is coming from one surface may not fall on other surface. Correct? Fully. So it is said radiant energy exchange between surfaces depend not only on the emissivity and temperature of the surface, it depends on the geometrical arrangement also. That is very important actually. Though the temperatures of the two surfaces are the same, what to say, for given temperatures T1 and T2, given emissivities epsilon 1, epsilon 2, the radiation heat exchange between the two plates will be different by simply varying the geometrical arrangement actually, right? So some factor should be there to take care of this, right? That factor is called shape factor, otherwise it is called as view factor or geometric factor, right? So shape factor is defined as the fraction of radiation energy which leaves one surface and strikes the other surface, right? The notation for a shape factor is capital F. If I say F1 to 2, that means it is a shape factor. It will give us the fraction of energy which is coming from surface 1 and falling on 2 actually. Suppose I say shape factor F2 to 1, that means F2 to 1 will tell me the fraction of energy which is coming from surface 2 and falling on surface 2. Sorry, surface 1. Clear? Yes. This is called shape factor. It's a very important factor. So it has to be calculated for any particular geometrical arrangement. So once you know the value of shape factor, the formula for heat transfer between two surfaces is Q is equal to F12 shape factor multiplied by epsilon bar into sigma into A area of the surface into T1 power 4 minus T2 power 4, while T1 is a higher temperature than T2. Here this epsilon bar is a value which has to be calculated based on the emissivities of the two surfaces, epsilon 1 and epsilon 2 actually. You can say it is the effective emissivity. I will explain in the next slide. So from this slide we come to understand that radiation exchange between two surfaces mainly depend on the geometrical arrangement of the two surfaces. Okay. Yes. Shall we move? But in reality, there are certain cases where the shape factor is equal to 1. I will explain. First case is two large parallel plates. I take two parallel plates having infinite area, very large plates, and they are parallel to each other. So our common sense will tell us that whatever energy comes from surface 1 will fall on surface 2 naturally. So we can say shape factor if 1 to 2 is 1. That means we can neglect shape factor. And both the plates are having same area because they are very large plates. So area A1 is equal to area 2. You can say that is equal to A, simply A. So heat transfer between the two surfaces is equal to, ignore F1 to 2, so simply epsilon bar into sigma into A into T1 power 4 minus T2 power 4. A is the area of both the plates. Here epsilon bar is equal to 1 by epsilon 1 plus 1 by epsilon 2 minus 1. So epsilon bar depends on epsilon 1 and epsilon 2. This formula is available in your data book. You can refer from the data book. Here, second case is radiation exchange from a very small object kept in a very large enclosure. Suppose a very big room is there and a very small hot object is kept inside. So radiation which is coming from the small object 1 will naturally fall on the inner surface of the enclosure. Right? Yes. So all the energy coming from the small object is falling on the enclosure. So we can say shape factor from 1 to 2 is equal to 1 actually. But the other it's from 2 to 1 it is not equal to 1 actually. So from 1 to 2 it is 1 actually. All the energy which is leaving surface 2 will not fall on object actually, small object 1. Okay, right. So shape factor from 1 to 2 is equal to 1 actually. Right. In this case, heat exchange Q is equal to epsilon bar into sigma into A1. Please note A1 is the area of the small object. Right? Into T1 power 4 minus T2 power 4. And epsilon bar is equal to 1 by epsilon 1 plus 1 by epsilon 2 minus 1 actually. Right. In the previous case, both areas are same. We are simply taking area A. Here we have to take the area of the small object A1. Third case is heat exchange between two concentric cylinders. I have a cylinder having radius R1 and outer cylinder having radius R2. So radiation energy which is coming from the inner cylinder will be falling on outer cylinder actually. All the energy which is coming from the inner cylinder will be falling on the inner surface of the outer cylinder. So we can say shape factor F1 to 2 is equal to 1 actually. Right. So Q is equal to epsilon into sigma into A1 into T1 power 4 minus T2 power 4, while A1 is the surface area of the inner cylinder. Okay. So A1 is 2 pi R1 into L actually. Circumferential area of the inner cylinder. And please note epsilon bar is equal to 1 by epsilon 1 plus A1 by A2 into 1 by epsilon 2 minus 1. While A1 is surface area of the inner cylinder and A2 is surface area of the outer cylinder. A2 is 2 by R2 into L actually. So this area ratio has to be considered while calculating epsilon bar. The last case is radiation exchange between two concentric spheres similar to cylinder. There is inner sphere, outer sphere is there. Inner sphere is having a radius of r1, outer sphere is having a radius of r2. So whatever energy which is leaving the inner sphere will definitely fall on the inner surface of the outer sphere. So you can say shear factor 1 to 2 is equal to 1 actually. So similar to cylindrical case, we can say Q is equal to epsilon bar into sigma into A1 is small area, that is area surface area of the inner sphere, into A1 into T1 power 4 minus T2 power 4, and epsilon bar is equal to 1 by epsilon 1 plus A1 by A2 into 1 by epsilon 2 minus 1. Here we have to be very careful. In the case of cylinder, area is 2 pi r into L. In the case of sphere, it is 4 pi r1 square for inner area. For outer area, it is 4 pi r2 square. So this is the difference you have to make a note actually. Again, these formulae are available in your data book. And another important concept, radiation shield. Suppose I have a plate, a surface plate at a temperature of T1, it has got an emissivity of epsilon 1. I have got another plate at a temperature of T2 and an emissivity of epsilon 2 actually. So there is a radiation heat transfer between 1 and 2 actually, right? I want to reduce the heat transfer between 1 and 2. So it can be accomplished by keeping a very thin sheet of very high reflectivity. There is rho, very high reflectivity, or you can say very low emissivity. Epsilon should be very low. If we keep such a thin sheet in between, it is understood that the heat transfer between 1 and 2 is reduced significantly. Such thin sheets are called radiation sheets, something like insulation in the case of conduction or convection. So radiation heat transfer between two surfaces can be reduced greatly by inserting a thin high reflectivity or low emissivity sheet of material between the two surfaces. Such highly reflective thin plates or shells are called radiation shields. The temperature of the radiation shield is T3 and emissivity of the shield is epsilon S. So here is a formula for calculating the heat transfer between the two surfaces 1 and 2 in the presence of n number of sheets. You can have 1 shield, 2 shield or 3 shield, right, between surface 1 and 2. Suppose you have n number of shields, so this is the formula. Q is equal to A into sigma into T1 power 4 minus T2 power 4 divided by 1 by epsilon 1 plus 1 by epsilon 2 plus 2 times n divided by epsilon s minus n plus 1, where n is number of shields, where you have 1 or 2 or 3 or 4, and epsilon 1 is emissivity of the first surface, epsilon 2 is emissivity of the second surface, while epsilon s is the emissivity of the shield, radiation shield. Naturally, you will find that heat transfer is significantly reduced. But practically, it's not advisable to have more than 3 sheets because the improvement in the insulatory effect will not be that high actually. So at best you can have 3 number of sheets. That itself will be good enough actually. Right. So before solving problems in the next session, please go through this video again, try to understand, so that you will be feeling convenient to solve numerical problems in the next session. Okay. I will meet you in the next session.